Hey, today we're going to be taking a look at a physics problem. We're going to be adding vectors, so it's going to be a vector addition problem using the component method. So I will read through the problem and then we'll solve it together. So an ant travels at 6.7 meters east, 25 degrees north, and then 4.3 meters west, 64 degrees north. Find the ant's total displacement using the component method. So as always with any kinematics problem, I'm going to draw out my compass and I'm going to state that my north and east directions are positive and my south and west directions are negative. Now you could also always use forwards, backwards, right, left, whatever you prefer. I like to stick with the north, south, east, west. So I'm also going to state by maybe classifying my two vectors, right? So I want to add these vectors, but I'm just going to classify here that vector 1 is 6.7 meters east, 25 degrees north, and my vector 2 here is 4.3 meters west, 64 degrees north. So what the question is just asking us to basically add these and find kind of the displacement in which our ant started at and where it ended at. And we can find that by adding these two vectors together. So now let me draw the two vectors just so we can visualize them. So we're going 6.7 meters east, 25 degrees north. So that's going to look something like this, right? Our angle here, right? We're moving east and then, so we're going in the like eastward direction, 25 degrees north above the horizontal, above the east axis, or the x-axis in this case. And this is this vector here, this is 6.7 meters. And vector 2, we're going 4.3 meters west, 64 degrees north. So we're going something like this here, right? 4.3, something like that. Okay? And this angle here is 64 degrees. Now when I want to start adding these together, I'm going to actually evaluate I need to evaluate the x and y components of both vectors separately, because I can only add the x components together and the y components together. And then I'll show you how we can kind of combine everything at the end. So I'm going to classify this, since it's the x-axis, I'll call that x1 since it's vector 1 here, and then this will be y1, and then same thing here, I'll call this x2, and this one here y2. So I'm basically splitting my vector into two components now. So this vector 1 into x1 and y1, and then vector 2 into x2 and y2. So now if I want, let's call this, I want to find xt, so my total x, okay? And I'll get that by adding, right? This will be equal to my x1 plus my x2. Now I'm putting these as vectors because the direction does matter here, right? So initially, right, I'm going, my x is in the eastward direction. So my x1 is going to be positive, but with the second vector, I'm moving in the westward direction, right? My x here is moving in the westward direction, so x2 will actually be negative. So this will be how I can state my total displacement in the x. And so to find this, I'm just going to plug in my values, right? But what is my value here? So we're going to be going back to trig, right? We'll use our SOHCAHTOA method or however we go about to solve our triangles, right? So for my x1, my angle of interest here is 25 degrees, right? And so because this is my angle of interest and this is the adjacent side with respect to my angle of interest, I'm going to use cosine. And just to give you a quick refresher on the side here, we know that cos theta equals our adjacent, I'll just call that A, over our hypotenuse, okay? So my hypotenuse here is 6.7, so to solve for A, I'm just going to plug in my hypotenuse and rearrange this, right? So it looks like H, just multiply both sides by H, right? To get H cos theta equals A. And in this case, A is x1. So I could say that x1 equals my hypotenuse, which is 6.7, cos our angle, which is 25 degrees. So I'll just plug that in here. Our x1 is 6.7 cos 25 degrees minus, same thing for x2. Let's go take a look at this. So x2 here, that's our, again, with respect to our angle of interest, which is 64 degrees, x2 is our adjacent side. So again, I'm going to use cos, and exact same thing, right? It'll just end up being hypotenuse times cos theta. So I'll say x2 equals my hypotenuse, which is 4.3 cos 64 degrees. And I'll plug that in here. And when I put that in my calculator, I'm going to get 4.187. I'll take 3 decimal places here. And I got a positive value, so that'll tell me that my overall displacement in the x dimension is going to be towards the east. Now I'm going to do the same thing for y. I'll call this total y, so total displacement in the y. And then same thing, right? y1, and I'll take the vector plus y2. Take them as vector values, right? Again, the direction matters. Our y1, we're going north, right? It's overall moving north, so that'll be positive y1. And then same thing with our second vector, right? We're also going north there, so this will be plus y2. Now, our y1 within our first vector, right? Now with respect to our angle, it's the opposite side. So I'm going to use, again, SOHCAHTOA. So SOHCAHTOA tells me that sine theta equals our opposite side divided by our hypotenuse. And same thing like we did here, multiply both sides by h to isolate for the opposite side. So that'll give me h sine theta equals our opposite side, and our opposite side here is y1. So I'll just say y1 equals h, which is 6.7 sine 25 degrees. Same thing for y2, right? y2, our hypotenuse is 4.3 sine, because y2 is still the opposite side to our angle of interest. It won't always be the same, right? Here, both y's are using sine, and here both x's are using cos, but this could change, right? It's important to understand the angle of interest, right? Always go with respect to the angle of interest. So sine 64 here. And same thing as before, I'm going to plug my values in. 6.7 sine 25 plus 4.3 sine 64. Okay? And when I plug in my values into my calculator, I'm going to get positive 6.696. And again, this is positive, which makes sense because overall looks like I'm moving in the north direction, right? If I'm to kind of put these two together, which is also a good strategy, which I can do right now quickly, right? So if I'm to take this vector, take vector 1, right? Take vector 1 and then add it to, right? Just on the tip of this, add our vector 2 to it. My resultant vector should look something like this. So if this is 1 and this is 2, this should be what my resultant vector should look like, which kind of makes sense because if I'm looking at this, right, it's moving eastward and it's moving northward, right? But we'll fully solve this in a moment. So now I have xt, so xt in my x. Now what I'm going to do is I'm going to actually take my two dimensions and put them together. So let me make a little bit more room here. And now what I'll do is I'll draw these out. So my xt is 4.187. So I'll just draw it like such. 4.187 meters this way. And then my yt, right? My yt is 6.696. So something like this. And I'll call this yt. I'll call this xt. And so the vector which I care about, which was in the diagram previously shown you there, is this. This is my resultant vector. This will give me my total displacement using the component method. So now what I can do, right, I have xt, I have yt. I want to find this. Let's call this A, just for the ant's total displacement. So I can say, again, using Pythagorean theorem, right, I can solve for this hypotenuse. So I'll say a squared equals xt squared plus yt squared. And so I know yt is this value here, xt is that value there, and I can just plug in and solve, right? So I'll have 4.187 squared plus 6.696 squared equals a squared. And then I can square root both sides, right, as well, to cancel out this square root, which when I plug it into my calculator will give me a equals 7.897. Now I got the magnitude for this, right? But I also need to solve for this angle to fully solve for that displacement, right? Displacement's a vector quantity, so I also need to solve for the displacement. Now, how I'm going to do that, right? I can take my angle, and I've got my opposite, and I've got my, there's different ways we can use, but I've got my opposite, I've got my adjacent. I'm going to go with what I've already solved for. So I'm going to use tan, right? Because the tan ratio tells me that tan, our angle, is equal to the opposite side over the adjacent side. If you're going based on SOHCAHTOA, right? It's TOA, so tan opposite over adjacent. And then to find the angle, I'm going to take the inverse tan, right? Move my tan to the other side. My opposite, which is yt, and then my adjacent, which is xt. So that's, right, yt 6.696 divided by 4.187, which will give me an angle of 58 degrees rounded up. Okay, so now I've got my magnitude, I've got my angle. So now what I can write is, therefore, the ant's total displacement is 7.897, but we will check our significant digits, right? The minimum is 2 significant digits, so I'm only going to take 2. We'll round this 8 up to 9, right? So therefore, displacement of the ant is, I'll just call it A like we have been before, A equals 7.897 9 meters east, right? We're going east. This angle, 58 degrees up, 58 degrees north. Not too complicated of a problem here, but there are a lot of steps. If you have any questions or comments, let me know, and I hope this helped.